Hello again, this is Puya. In this lecture, we're going to talk about binary trees. So, as discussed in the previous video, binary trees are a special class of trees that every node has maximum 2 children, or maximum degree of nodes is 2, right? Recursive definition for binary trees that a binary tree is a finite set of nodes that's either empty, right? So even an empty tree is a binary tree, or consists of a root and 2 disjoint binary subtrees called left subtree and the right subtree, which they can be also empty, right? So like we don't have to have both left and right subtree. We can just like have left or right or none of them, which is going to be the leaf nodes. So a binary tree is composed of 0 or more nodes, may be empty. If not empty, has a root node. Every node in the binary tree is reachable from the root node by a unique path, and a node with neither a left child nor a right child is called a leaf, right? These are the coming from the definition of a tree. But the main thing that we have to know for a binary tree is that every node has maximum 2 children. So the degree of nodes are either 0, 1, or 2. This is an example of a binary tree. A is the root. It has 1 child. So like we can consider the whole thing here. It's the left subtree of A. Okay, and its right subtree is empty. B has 2 children, right? So this is going to be its left subtree. This is going to be its right subtree. E has 2 children. K has only 1 child, right? So this is its right subtree. Its left subtree is empty. L and F, G, M, and J are leaves. So they have 0 children. So no left subtree or right subtree. And similar for the other ones. Like if you find the degree of every node, it's either 0, 1, or 2, right? So this is a binary tree. This is also a binary tree, and this is a special binary tree. If you remember, this is a complete binary tree because in the second to the bottom level, the second bottom level, right, we have the maximum number of nodes possible. At level 2 or depth 2, we can have maximum 2 to power 2, 2 raised to power 2 number of nodes, which is 4, and we have all of them. And the leaves at the bottom level are as far to the left as possible. Also, the first condition was that the leaves have to be maximum 2 different levels, right? Which is the case here, right? It satisfies all the 3 conditions, so it's a complete binary tree. Any complete binary tree is also considered balanced. So this is a balanced binary tree as well. These 2 examples are also special kind of binary trees. There are binary trees, right? You can see that other than the leaf, every node has only 1 child, and here like they're all left child, like left children, right? So this is called a left skewed binary tree, and this one is called a right skewed binary tree. Okay, but this one is very unbalanced. Okay, it's unbalanced tree. A full binary tree, it's a binary tree that all the leaves are at the same level, and we have the maximum number of nodes at every level. So at level 0 we can have only 1 node, which is the root. At level 1 we can have 2 raised to power 1, 2 nodes, which is what we have. At level 2 we have 4. At level 3 we have 8. So this is a full binary tree. Any full binary tree is also complete, right? So this is also complete binary tree. It's also balanced, right? You see that like all the nodes, like the distance to the root, or almost at the leaves distance to the nodes are almost like this, exactly the same. Like here, like you can see that also, like the left and right subtree of every node, their height are the same, right? So this is a balanced binary tree. This one is a complete binary tree. We mentioned like what a complete binary tree is, right? So this is a complete binary tree. It's a balanced one as well. An application of binary trees can be um, expressing arithmetic expression, algebraic expressions, right? So you can see an example here. In these kind of problems, all the internal nodes will be the operators, and the external nodes or the leaves are the operands. Okay, and what we'll talk about traversal through a binary tree later on. We'll see like how if we traverse through all the nodes of this tree, we can have infix, postfix, or prefix notation of this expression. Another application of binary tree is having decision trees. So this can be like basically like important in problems that we have to implement algorithms, or like when you have like AIs, like robots that you want to have like a different orders to be executed like based on like specific conditions, right? So like here in a decision tree, the internal nodes are questions that have a yes or no answer, right? So here, if your answer is yes, you go to the left, right? So like if the answer is no, you go to the right. You have to be consistent in that notation. And the internal nodes are the questions, yes or no, with the yes or no answer, and the external nodes are the decisions that you make based on the answers that you have, right? So this is one of the examples, right? So like you can implement algorithms and like can have applications in AI, artificial intelligence. Okay. You remember that we mentioned that for any tree, if you have n nodes, you have n minus 1 edges, right? So let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a tree of size 10. It has 10 nodes. How many edges do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is always the case. It's not a coincidence. Okay, in a binary tree, the depth of the tree, which is the same as the maximum depth of like leaves, right? So and it's also like the height of the root. The depth of the tree is the same as the height of the root or height of the tree. Okay, the maximum number of leaves that you can have is 2 raised to power depth. The maximum number of nodes that you can have, it's 2 raised to power depth plus 1 minus 1. Okay, and maximum depth that you can have, it's n minus 1, right? So like this would be the case for a skewed binary tree, right? That you would have the maximum depth possible. Okay, you can verify all of this, right? We're gonna see like more about these first two properties, but this one, it's easy to verify, so you can verify it yourself. We talked about the concept of balance, the exact definition, like it might have like the like variation based on specific balanced binary tree version that you are implementing. So this is a balanced binary tree, right? So if we talk about the like height balanced or AVL trees, like you can see that the height of left subtree of every node and the right subtree of every node, the difference between them, it's maximum 1, right? So you can see that like for this one, the height of the left subtree is 1, its right subtree is 1, so the difference is 0. That's good. The same thing here, the height of the left subtree is 2, its right subtree is 1, the difference is 1. For this one, the height of the left subtree is 1, 2, 3, it's 3. The height of its right subtree is 1, 2, 3 as well, the difference is 0. And you can verify that for every other node. This is a balanced binary tree. This one is not balanced. Let's look at, for example, this node, right? right? The height of its left subtree is 2. The height of its right subtree is 1, 2, 3, 4. The difference is 2, right? So this is not a balanced, height balanced binary tree. This can be also, like, you can also use this node to verify that, and or even this node to verify that. If like this property is not valid for any node, for even like a single node, means that it's not a balanced tree. In most applications, we want to have a reasonably balanced binary tree, because it means that like we can just like search through the tree, or we can insert elements or delete elements very efficiently compared to an unbalanced binary tree. We're going to see more about this when we talk about AVL trees, LVL binary search trees. Two other concepts which are not frequently used, but like it's good to know, similar binary trees like are binary trees that they have the same topology but different node elements. Like here, like you see that like the topology of the tree are the same, right? So they're similar, right, because they have the same structure, but they don't have exactly the same values, right? So like not necessarily the same values. These are similar. Or just like we can have like we can have copies of binary trees. Two binary trees are said to be copies of each other if they have similar structure and same content at the corresponding nodes, right? These two are copies of each other. Complete binary tree. So we mentioned like about the conditions for having a complete binary tree. So in a complete binary tree, every level except possibly the last one is completely filled, right? Second, all nodes appear as far to the left as possible, right? In the last level, right? So this is basically what we have. And in a complete binary tree that we have here, for example, there are exactly n nodes, and level R of t can have at most 2 raised to power n nodes. Okay, so we already mentioned about it, right? At level 0 we can have like 1 node. At level 1 we can have maximum 2 nodes. At level 3 we can at level 0 1 node. At level 1 2 nodes. At level 2 4 nodes. At level 3 maximum 8 nodes. This is basically what is discussed here. Okay, now there is a convention to name the nodes or number the nodes, that you go like through levels, and you go from left to right at each level, and then you go to the next level. So 1 2 3 4 5 6 7 8 9 10 11 12 13. If we number the nodes like this according to this convention, we can find the parent or child of every node using these formulas that are given here. Okay, it's very easy to verify. This is only true for a complete binary tree though. Like it's just like it's not true for any binary tree. Has to be complete. Okay, if you know that the height of your tree is h, okay, if you know that the height of your tree is h, the minimum number of nodes is h plus 1. This is the case where you have a skewed binary tree, right? So you see that here the height of the tree is 3, and we have 4 nodes, right? This is like the minimum number of nodes that you can have for a binary tree of height 3, okay? The maximum number of nodes that you can have for a tree of height h, right? For a tree of height h, the maximum number of nodes, it's going to happen when you have a full binary tree. Okay, it means that you have maximum number of nodes at every level. Okay, so in that case, if the height of your tree is h, right, then you would have 1 plus 2 plus 4 plus 2 raised to power h, right? So this is the maximum number of nodes that we can have for a binary tree of height h, and it's gonna happen if your tree is full binary tree. Okay, so this is like a series, and then you can just like basically calculate this very easily. I just like put the formula here. If we consider this summation as s, if we multiply it by 2, we have 2s is going to be equal to 2 plus 4 plus all the way to 2h plus 1. This part of it, it's going to be s minus 1 plus 2 raised to power h plus 1. So 2s is equal to s minus 1 plus 2h raised to power h plus 1. So it means that s is going to be 2 raised to power h plus 1 minus 1. Okay, so if you have n nodes in your tree with the height h, in a binary tree with height h, n is going to be between h plus 1 and 2 raised to power h plus 1 minus 1. Okay, and it's like you can also like say the other way around. If you have a tree of if you have n nodes, the height of the tree, right, can be between n minus 1 and log 2 of n plus 1 minus 1, right? So you can find the limits, the upper limit and the lower limit for the height or node. If you have the other parameter, if you have the height, you can find the upper and lower level for upper or lower limit for the number of nodes. If you have the n, you can find the upper and lower limit for the height. Okay, if you have a full binary tree, then you have the maximum number of nodes, which is going to be 2 raised to power h plus 1 minus 1. In a complete binary tree, every level except possibly the last one is filled, and all the nodes in the last level are as far to the left as possible, right? And can have like between 1 and 2h nodes at the this is 2 raised to power h, sorry, 2 raised to power h. Oh, sorry. I'll fix this later. Let's just like write it like this: 2 raised to power h. Okay, this shows also like a different complete binary trees that we can have right here. Like if you have one node, empty is like empty tree is also complete. One node, this is complete, this is complete. 3 nodes, this is complete. 4 nodes, this is complete. 5 nodes, this is complete. 6 nodes, this is complete. 7 nodes, this is complete, and 8 nodes, this is complete. So it basically shows you how you can just like grow a complete growth of this. Basically demonstrates like the growth of a complete binary tree based on the number of nodes that you have in your tree. I mentioned about like numbering convention for the nodes. We just like number them from 1 all the way to maximum 2 raised to power h plus 1 minus 1, right? So here like would be 2 raised to power 4 minus 1, which is 15. And the naming convention or the numbering convention is that like we start from level 0, right, and we go from left to the right. Okay, so that's, if that's the case, we can find the child-parent relationship very easily, right? If we know that there are like we have node I, we can find its parent, right? If we have like also like we know that like we have node I, we can like find its left child or right child based on the given formulas. Okay. I'll skip through this because these are like very easy to verify. So, and they're not as important, right? So like let's go through this very quickly. How can we represent a binary tree? There are two different representation methods. One of them, it's called like implicit representation or sequential linear representation using arrays, and explicit representation using like linked representation, like something similar to doubly linked list, like similar to like what we had in a double linked list with using pointers. Let's first go through the array representation. So this representation is static. You just allocate a block of memory before storing the actual tree. And once the memory is allocated, the size of the tree will be fixed. Nodes are stored level by level, starting from the 0th level all the way to the last level, and you go from left to right. Root node is always stored in the starting memory location as the first element of the array. Okay. So I'll show you like how this is done using an example, but like this basically shows you some of the rules that we have in the sequential representation. The root is always at location 1, right? Here, like location 1 in C++, that would be like for an array would be index 0 of the array, okay? So here, like just like be careful that here when we talk about location 1, means like the first element of the array. It's not necessarily index 1, right? It's definitely not index 1 in C++, right? So here, like all these ones are like for location numbers. Now, let's see through this example, how can we store, excuse me, how can we store this 3 in an array? So let's say that we already have fixed the size, right? So we go through every level, right? 45 goes in the first element. It's like location 1, but index 0, right? Don't just like mix them up, right? This is location 1, but not necessarily the same index. Like in C++ and most of programming languages, indices starts from 0, right? And then we go to the next level, 22 and 77, right? This level is like has the maximum number of nodes, right? Then in this level, level 2, we have 11, 30, but this node doesn't have a left child, so we leave it empty, or like using null, or like something that like just like basically to know that this is empty. And 90 goes next. In the next level, again, like we go from left to all the way to the right. This node doesn't have a left child, so we have to leave it empty. Then it goes 15, 25. Again, this one is missing the right child, doesn't have a right child, so empty. Okay. And this one was supposed to have, like, if you consider a full binary tree, this one would have a left child and it would have 2 children, right? So we also have to put two more empty spots here, and then it goes 88. Okay. So basically what you can do is basically allocate memory for an array of like size, let's say 2 raised to power h plus 1 minus 1 for a full binary tree, right? But you fill the array like level by level from left to right. Okay, and you see like already one of the disadvantages of this representation. It's like many of the memory locations are not used, so it's not very memory efficient. Okay, another example here, like this is like an arithmetic operation, right? So plus, minus, asterisk, a, b, c, slash. Okay, so here empty, 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 and then d and e. Okay, so you see like we have many empty spots here. Okay, so another one here, for example, here right, that the height of this is 3. 2 raised to power h plus 1 minus 1 would be uh, like basically 15, right? So that's what we have here, right? So that's what we have here. So then how we store it, like level 0, like the root always is first one, then B, C, then empty, 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 then D, right? Then empty, 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 and then E. Okay, see that, like if we don't have a full binary tree, most of our array, or like many of the memory locations, are going to be empty, right? In this case, so can allocate 7 elements, like for our array, right? Go like A, then B, C, then D, E, empty, and then F, right? So this is like how we can um, represent a tree using arrays. Some of the advantages is that any node can be accessed from any other node by calculating the index, right? So we just like can find like the left child, right child using the index. Okay, and the data are stored simply without any pointers. We don't have any pointers, right? So in some programming languages, like we don't have like pointers, right? So like BASIC or Fortran. So this representation would be suitable for those languages. Inserting a new node and deletion of an existing node is easy, right? So disadvantages, right? Majority of the array entries might be empty. Okay, also like have only static representation. It's not possible to enhance the tree structure if the array structure is limited, right? So like it's not possible to expand the tree, basically. That's what it means. So here, like again, like it shows the formulas that you can have to find the left child of node with at location I. Again, be careful that like when we say location I, it's not the index I, right? So like if you want to use index of the array, right, you have to modify these slightly. Okay, so you can do that yourself, right? But this is location I, which like starts from 1 instead of 0. Okay, you can find the right child, you can find the parent, and if you know the depth or the height of the tree, you know exactly maximum size of the array that you have to allocate. Okay, so this is an example for you. Draw the tree structure whose array representation is given, right? So can you guys like draw this binary tree that this has like this array structure? Okay. Now the second method for representing the binary tree is using linked representation. It's similar to what we had in doubly linked list, right? So every node is represented as like basically a structure, right? It's like a node structure, right? Similar to a doubly linked list that we had 2 pointers, right? But that was pointing like to the previous node and the next node. But here, like we have a pointer that points to the left child and a pointer that points to the right child, right? So we see that like we have the data part, we have the left child and the right child, and like you might have like other constructors and different things that you have here. So this is the like the excuse me, this is the linked representation. Instead of pointers, you also can have references, right? But the pointer is more common. And in this case, the memory space required for a tree of size n with n nodes, right? It's going to be n multiplied the space required by one node, right? We don't have any empty memory spaces as we did in the array implementation. Okay, So this is like the linked representation. It's more frequently used. It's like more advantages compared to the array implementation. The array implementation, like it's also going to be useful in some applications. So here you see that an example of like how we can represent a tree using linked representation. We always have a pointer that points to the root node. Like if you remember like the linked list concept, we always had a head pointer, right? That was a pointer that pointed to the head of the linked list, right? In the tree we have a root pointer, right? Which is going to be of type node star, okay? Node pointer. And here you see that, for example, this node, the left child pointer is pointing to B, the right child pointer is pointing to C, and similarly for other nodes. Okay. And here, for example, this pointer is null, this pointer is null, this pointer is null. These two for this node, both of the pointers are null. The same similarly for F, for this node, the pointers are null, but the data value is equal to character F. I already mentioned in the previous video some of the member functions or some of the operations that you can have for trees. Some other binary tree operations are finding the height, finding the number of nodes, making a clone of your tree, determine if two binary trees are copies or clones of each other, and display the binary tree, basically traverse through every single node, display it, evaluate the arithmetic expression represented by a binary tree, and these ones are related to this example as well, like obtain the infix, postfix, prefix of an arithmetic expression. So these are some of the binary tree operations you can have. This is all like showing like an example that shows like how we can represent this tree using a linked representation using pointers. We have a root pointer that points to the root right here, like it's a left child pointer, right child pointer. This like convention is not very used like in graphically. You usually put the left child before the key value and the right after it, but like this is basically the first pointer is left one, the second one is the right one. The right pointer of this node is pointing to the node with element C, right? And the left pointer of C is null. And similarly for the rest of the nodes, you can see like how the pointers and the data values are filled. Another example showing like how we can represent this tree using a linked representation. Again, another example here. This is an arithmetic operation. Again, like I'm gonna talk about traversal of a tree later, so we can just like see what these like member functions are in the next video. You can find the size, you can find the height, you can find the depth, and different accessors or getters that you can have for your tree class. Like mutators, you can have like add a left node for a node, add a right node for a node, or like other things like. And like you can see that you can have like a constructor, destructor, like you can have an isEmpty function, insert item, retrieve item, print the tree, delete an item. Okay, and like the in the class, the tree class that you have, like you need to have a root pointer that points to your root, and similar concept that we had for like the linked list, that we had a head pointer. Okay. So like as an example, I want you to represent these trees, these three trees using arrays and linked list, and show it like maybe on a piece of paper. Thank you so much. I'm going to continue this in another video. Thank you.